Okay, it's Brian, and we're going to be talking about the material of Chapter 16. And in Chapter 16, we're going to be looking at superposition, and particularly we're going to be looking at the idea of standing waves. And we're going to be looking on standing waves in strings and in pipes, and we're going to look at resonance of systems, particularly your vocal system. And the big question we have is what happens when two waves hit each other? And we're focusing on sinusoidal waves. So let's suppose we've got two sinusoidal waves. Now in the chapter, you've had a chance to take a look at two different cases where we have a case of constructive interference. And that is I have one wave and a second wave. So here's my first wave. And my second wave is shifted by 0, 1, 2, or 3 wavelengths from it. When you do that, you end up having crests meet crests. And the displacement of the medium is the sum of the displacement of the two waves individually. It's just going to be double the displacement of either wave. And so I end up with a so-called constructive interference. I end up with the two waves adding. And I get a bigger wave than I would have had with either the two individually. Case we look at is destructive interference. So if I've taken one of the waves and I've shifted it by a half, 1.5, 2.5 wavelengths, then I have a crest meet a trough, and so one of them is pushing up, the other is pushing down. The sum of those two is 0, and I have the two waves completely canceling each other. That's a so-called destructive interference, and you get that when you have half wavelength shifts, okay? So let's look at some situations, and let's say, suppose I have two sources of sound. Oh, and by the way, I'll mention, we're doing this with sound because it's kind of like easier to wrap your mind around, but next semester we're going to do this with sources of light. And we're going to start in Physics 122 by looking at that very situation. So that's where we're going to pick up when the story continues. So I'll refer back to these sort of things. But suppose I have two sources of sound. Okay, and so I have speaker 2 and speaker 1 making sound, and I ask what is the sound at this point, or if I have two sound waves from two speakers, not in a line, but kind of like next to each other like this, and we ask what is the sound at this point, what I look at is the path length difference. I say, how far did the wave from speaker 1 travel to get to that point? And how far did the wave from speaker 2 travel to get to that point? And then I'm just going to look at the difference. What is the path length difference? And we're going to call that delta D. And if the path length difference, delta D, is a multiple of the wavelength, so m times lambda, where m is equal to 0 times 1 times 2 times 3, etc., 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 this m is going to be what we're going to call an index variable. If that's true, I get constructive interference. If I have the path length difference is equal to m, my index variable, 0, 1, 2, 3, etc., plus a half, okay, then I'm going to get destructive interference, and the displacements will cancel. Now let's look at a specific case of this, okay? So suppose I have two speakers emitting identical sound waves with a wavelength of 4 meters. The speakers are 8 meters apart, directed toward each other as in the diagram. So we're going to look at point A and ask a couple of questions. First, what is the distance from the left speaker? Second, what is the distance from the right speaker? Third, what is the path length difference? And then, will the sound be loud or soft? So here we are with the left speaker. As the wave travels from the left speaker to point A, the distance is 2 meters. If we're going from the right speaker to point A, the distance is 6 meters. And so the path length difference, delta D, is equal to 4 meters. And as a consequence, that's going to be a loud spot, because delta D is equal to 1 times lambda, because lambda is equal to 4.0 meters. And so the two waves will be exactly in phase with each other, and so I'm going to get a loud spot right here at point A. Next, let's look at the situation at point B, and we'll ask the same questions. The distance from the left speaker to point B is 3 meters. The distance from the right speaker to point B is 5 meters. The path length difference, delta D, is equal to 2.0 meters. Well, that's equal to 1/2 wavelength. And so the waves will be exactly out of phase with each other. When the waves get to point B, the crests from one wave will be meeting the troughs of the other. And as a consequence, this will be a soft spot. The waves will cancel at that point. And now if we look at point C, Okay, at point C, clearly it's 4 meters from the left speaker, it's 4 meters from the right speaker, so the path length difference is 0, and so the two waves will exactly overlap. Crests meet crests, troughs meet troughs. This will be a loud spot. Okay, we're going to do a lot of stuff like that in the second semester when we're going to be concerned with light waves, and this is a much more important phenomenon when you're talking about light waves. Now here's a physical implementation of this very thing. So here's my friend Dave Maiulo, who teaches at Rutgers, and he's got a long tube with propane gas inside it, and there's a speaker at one end and there's a speaker at the other end, and he puts the same frequency in both speakers. And so I have a wave from the left speaker traveling one way through the tube, and I have a wave from the right speaker traveling the other way through the tube. And where the waves overlap, you get constructive or destructive interference. And in regions where I get constructive interference, like this point right here, I get big waves. In regions where I get destructive interference, I get small waves, and so I don't get very much gas coming out, so I get small flames. So I have regions of constructive interference where the waves are big and the flames are shooting out, and I get regions of destructive interference in between. And that's the very situation that we have right here. Now let's look at a problem in 2 dimensions. So suppose I have 2 speakers, speaker 1 and speaker 2, and they're emitting identical sinusoidal waves, and they're in phase with each other. And you have these 2 speakers are 4 meters apart. The grid here is 1 meter squares, okay? And the question is this: if someone walks on a line in front of the 2 speakers and measures a quiet spot, and then a loud spot, and then a quiet spot, these are clearly regions of destructive interference, and then constructive interference, and then destructive interference. The question is, what is the wavelength of the sound from the 2 speakers? That's the question we want to consider. Now to do that, we're going to do some calculations. First off, we're going to look at the distance from the speaker 1 to the left quiet spot, the distance from speaker 2 to the left quiet spot. We're going to determine the path length difference. And let's just do that, and then let's come back and think about this. Okay, now, the distance from speaker 1 to the quiet spot is 3 meters. Okay, we can tell that that's just 3 lines. The distance from speaker 2 to the left quiet spot, what is this? Well, check this out. I'm going to write a triangle like this, and this is clearly a right triangle. This side of the triangle is 3 meters long. This side, the lower side of the triangle here, is 4 meters long. This is a 3, 4, 5 triangle, so the hypotenuse is 5.0 meters. So the path length difference, the difference in distance traveled by the sound from speaker 1 and the sound from speaker 2, is just 2.0 meters. Okay? And you were said here this is the first instance of destructive interference, and that's why. Suppose you had someone standing at the loud spot. Well, clearly the distance to speaker 1 and speaker 2 is the same, so the path length difference is 0. And then they start to move to the left. So they start to move this way. The 2 waves are going to begin to get out of phase, and the first place they get out of phase is right here. This is the first quiet spot. So at that first quiet spot, the path length difference, delta D, is going to be equal to 1/2 of the wavelength. Oh, and we know what delta D is. That's 2.0 meters. So 2.0 meters is 1/2 of the wavelength. And so as a consequence, the wavelength is 4.0 meters. That is the wavelength of the sound to produce this particular phenomenon. And as I say, we're practicing this now. This will be really, really, really important when we get to talking about light waves in the second semester. Now, let's talk about something else we'll look at in the second semester, which is kind of amazing. This is a picture of someone who is a group of investigators were taking 2 beams of neutrons and overlapping them. And there are places where the 2 beams experience constructive interference, and there's regions where you experience destructive interference. So I get constructive, destructive, constructive, destructive, and I'm actually having the beams interfere with each other, constructive and destructively. That tells me that the matter in the beams, the neutrons, are acting like waves. And this is kind of amazing, and it's something we'll talk about when we get to the second semester. And matter has this wave character associated with it, and this is one of the clearest indications. Now suppose I have this situation. Suppose I have two speakers that are making sounds, and they're complex sounds. This is not just a simple sine wave, that's a sum of sine waves. So speaker 1 and speaker 2 makes a wave which is just exactly inverted. So I took the wave from speaker 1 and I made a wave from speaker 2 that is exactly the same but upside down. The sum of those two waves is just going to be 0. It doesn't matter what shape the wave has. If they're exactly opposite each other, the sum is 2. And that is how you make sound-canceling headphones. And here's a picture of some engineers working on the first versions of these. What happens is this. If you have your little earphones here that you're wearing, okay, you have a microphone on the outside that samples the sound in the room. And then inside the headphones, it makes a sound which is exactly inverted. So if it's sensing this wave on the outside, it produces a wave on the inside that is exactly the same size, but exactly opposite it. And the sum of the sound from the outside and the sound produced on the inside is 0. So you actually produce sound inside the headphones, but it cancels the sound from the outside. So adding sound produces a lower sound intensity on the inside. It's kind of magic. It's kind of magic. I love this. A place where this happens is in loudspeakers. So if you open up one of your speakers and in one of your devices, or if you actually have bookshelf speakers, there's a little paper cone that's pushing air back and forth here. The little paper cone pushes air back and forth. But check this out. It's making sound waves from the front because it pushes out and then it pulls in. But in the back, it's pulling in and then it's pushing out. It's exactly out of phase. And so the sound from the front of the speaker and the sound from the back of the speaker are always exactly out of phase with each other. So anytime you see a speaker, you don't see it by itself. It's in a box. You have to do that. You want to prevent the sound from the inside and the outside from interfering with each other. And so speakers always have to come in some sort of box or some sort of enclosure. Now I want to talk about a phenomenon called beats. So suppose I have two waves coming towards somebody, and I have these waves here. One of them's in red and one of them's in orange, and they have slightly different frequencies. They start out in phase with each other, or so at this point they're in phase with each other. But if I move along the wave in the direction of their travel, since their frequencies are slightly different, their wavelengths are slightly different, there'll be a region where they're out of phase. Then there'll be another region where they're back in phase again. As that wave comes towards you, what you'll hear is loud, soft, and then loud. You're going to hear a beat between the two waves. And so you end up with a beat frequency, which is a difference of the two frequencies. And this is discussed in the textbook. And this is actually really, really important for a lot of detections of reflected waves. For instance, in class, we talked about ultrasound, and you bounce ultrasound off things. And when the ultrasound comes back, the frequency is going to be shifted if the thing that it bounces off is moving. And you can look at the difference in the frequency going out and the frequency coming back, and you can use that to determine the velocity of the thing that the waves is bouncing off of. For instance, this is how radar guns work. So a radar gun that the police use, they send out radar, and the radar comes back from bouncing off of a car, and it gets shifted to a different frequency. And then what the detector does is it measures the shift in the frequency that went out and the frequency that came back. So suppose, and these are real numbers, for a real radar gun, the radar sends out microwaves at 10.5 gigahertz, okay? And then the wave bounces off a car, which is coming toward the radar gun. And then it will measure the difference in frequency between the wave that goes out and the wave that comes back. And that frequency will be related to the speed of the car that the signal is bouncing off of. So the question is, if the car is moving at 20 meters per second, what will be the beat frequency? And let's solve this one. And the first thing we're going to do is strategize. And we're going to say this. Look, there's a wave coming out of the radar gun. So I have my radar gun over here. Okay? And then it hits a car. Okay, so here's my car. And the car is moving this way at a speed v. And so the reflected wave is going to be shifted to a higher frequency. And we're going to measure the difference in frequency between the wave that goes out and the wave that comes back. We're looking at the shift in frequency. And of course, the shift in frequency is just going to be produced by the Doppler shift of a wave reflecting off of a car. And for our preparation, we'll remember that the shift in frequency is 2 times the frequency of the source of sound times the velocity of the object divided by the velocity of the waves. So we can solve that for the shift in frequency, and let's do that on the next slide. Okay, so the shift in frequency is equal to 2 times Fs times v of the object divided by v. By the way, there was a plus and a minus here, and I chose a plus because when something is coming towards you, the waves that reflect from it are shifted to a higher frequency, just as in the homework problem with the bats on the last assignment. So I've got a plus sign here, but we don't need to put in the plus signs implicit. Okay, the frequency of the source is 10.5 gigahertz, so 10.5 times 10 to the 9th hertz. The speed of the object, it's the car that it's reflecting off of, is 20 meters per second. V is the speed of a wave. And what are the speed of microwaves? Well, microwaves travel at the speed of light, for which we use the symbol c. So this is 3.0 times 10 to the 8th meters per second. And you would think with that high speed, we're not going to measure very much of a shift in frequency, but there's also a very, very high frequency. And so you will get a small but detectable shift in the frequency. What we is 1400 hertz. Okay? And my assessment for this is I know that the way that police actually tune these devices is they put a tuning fork near them. And the tuning forks have frequencies which are in the audible range. And this is a frequency very much in the range of your hearing. And so we end up with a reasonable result that matches with our understanding of how the world works. Now I want to talk about standing waves, okay? So if I have a string that is stretched between 2 fixed points, the ends of the string can't move, and if you pluck it, you're going to get waves, but you can only have certain possible waves. I can have a wave that looks like this mode right here, and a wave that looks like this mode right here, or a wave that looks like this mode right here. I can only get certain possible standing wave modes. And we will see this in lab this week, and you will also have a nice video of it, which I will show at our in-person class. And the possible frequencies which you can get of the standing waves on strings. And I have f sub m. M is an index variable. Okay, and it takes the values of 1, 2, 3, 4, etc. The only possible frequencies I can get is m times v over 2l, where v is the speed of the wave and l is the length of the string. Those are the only possible frequencies that you can get. So let's do an example. And it turns out spiders actually tune their webs. They tune their webs, they adjust the tension, and they adjust the properties of the string so that the web is going to vibrate at a particular frequency to which the spider is very, very sensitive. And that just renders them more sensitive, which is kind of amazing. And the question asks this. There's a 12 centimeter long strand of string, of silk, and the waves travel at 330 meters per second, and those are reasonable values for a web spinning spider. Insect lands and excites the lowest frequency standing wave. Question, at what frequency will the strand vibrate? Well, our strategized step is we're going to say this. This is just a standing wave on a string, and we're going to solve this as a standing wave on a string problem. And for my preparation step, I'm going to remember that the frequency of waves on a stretched string is m times v over 2l, where m is equal to 1, 2, 3, 4, etc. But remember, we are only asked to find the lowest frequency standing wave. And so we only want m is equal to 1. We want the lowest possible frequency. With that in hand, we can solve. So we get the lowest frequency standing wave is equal to 1 times v, the speed of the wave, divided by 2l. So the speed of the wave is 330 meters per second. The length of the string is 0.12 meters. That's the same as 12 centimeters. And so I can calculate. If I do that, we get 1400 hertz. And here's my assessment. I've done this several times. If you find a spider that's spun a web and it's got a big web stretched between trees or whatever, if you come up to the web and you sing at it, and you give it some high pitch, like you go, oh, at the web, and you can go, oh. If you adjust the frequency, when you get it just right, you will hit the frequency at which the web likes to vibrate, and it will vibrate, and the spider will freak. I've had spiders drop off the web. They're like, I don't know what just hit the web, but it's a big amplitude of oscillation, and I am out of here, because the whole web is kind of like vibrating at this frequency. And I feel a little bit bad messing with spiders, but it's kind of awesome. And the frequencies that I have to do are in the range of 1400 hertz, so that result seems quite reasonable. Now here's a question for you. You know that you have a turntable inside your microwave oven. Why do you do that? There are hot spots and cold spots in the microwave, and why? Well, remember, if you have standing waves, and this is going to apply to microwaves as well as standing waves on strings, you can only get certain possible conditions. So inside a microwave oven, okay, you have microwaves, and those are electromagnetic waves. The intensity of the waves is 0 at the sides of the oven. Those are nodal positions, okay? Those have to be nodes. And so since that's true, I have to have nodes at the ends. I can only get certain possible frequencies of standing waves. And let's look at, for instance, this third wave right here. So I'm looking at m equals 3. So m equals 3 has got a node at the edge, as we know it must, but it's also got 2 other nodes in the middle. So those nodes are going to be cold spots. The intensity of the wave is really low here. In between it, I've got 2 regions where I've got antinodes. I've got really, really big amplitudes of oscillation. So at my antinodes, those are going to be hot spots, and my nodes are going to be cold spots. At the green dots, I'm going to have lots of heating, and at the red dots, I'll have very little. And you're going to have hot spots and cold spots inside your microwave. And they're a distance of about half a wavelength apart. So here's 2 waves. I've got this red, dark red one is 1 wave. Half a cycle later, it looks like this light red wave. And so you can see at these regions right here, I'm getting a lot of amplitude. At this region right here, I'm not. So I have antinodes by the first line, nodes at the second. The distance between successive antinodes we can see is half a wavelength. And you can also see that the distance between successive nodes is 1/2 of a wavelength of the wave. Now, let's think about this. Microwaves have a frequency of 2.4 gigahertz. That's a microwave. The microwaves in your microwave oven. Question, what is the wavelength? Well, remember, the wavelength is just equal to the velocity divided by the frequency. And the velocity of microwaves, as we saw before, they're electromagnetic waves. They travel at the speed of light, 3 times 10 to the 8th meters per second, dividing it by the frequency, 2.45 gigahertz, or 2.45 times 10 to the 9th hertz. I come up with a wavelength of about 12 centimeters. Okay? So inside your microwave oven, there are hot spots and cold spots that are about 12 centimeters apart. And if you put in, this is from a friend of mine, he put a paper towel inside a microwave oven, and then he turned it on and ran it. And there was you can see hot spots and cold spots. And the distance between successive antinodes, i.e. the hot spots, is half a wavelength, or about 6 centimeters. And the distance between successive cold spots, again, is about 6 centimeters. And so you get these hot spots and you get these cold spots. And you can see there's a nice cold spot in the center, and that is true with most microwave ovens. So when you put your stuff in the microwave oven, what you want to do is you want to put it on a rotating turntable so it rotates through the hot spots. You don't want to put it in the center of the turntable, as the people have done here. It makes a prettier picture, but you do not want that. You want it more on the outside edge, and as it rotates through, it goes through more of the hot spots. And so you get hot spots, cold spots, cold spots, but it doesn't just rest at a hot spot or a cold spot. You want it to move. And so that you don't get uneven heating. That's ultimately why you need a turntable in your microwave oven. Now the other thing I want to talk about is standing sound waves. Okay, if I've got tubes, I can have standing sound waves. And as you can read in the text, there's a difference in the modes for open tubes, closed tubes, and open-closed tubes. There's 3 different situations that we can have. And the 3 different situations end up having very, very different frequency relationships. And so if we're solving a problem having to do with standing waves in a tube, the first piece we have to do is we have to identify what are our boundary conditions, what sort of system is this. So let's look at an example. And it turns out your ear has high sensitivity at certain frequencies, and some of that is determined by the fact that your ear canal is a tube. And it's going to have certain resonances associated with it. There will be certain standing waves that can exist inside your ear canal. So we want to know what are the frequencies of the standing waves in your ear canal. And at those frequencies, you're going to get an enhanced amplitude of oscillation, and so you will have enhanced sensitivity. What will that be? Okay, for our strategized step, we have to determine what sort of system that we have. Okay, so your ear canal looks like this. Okay, it's a tube, and it's open at one end. That's where it's open. And then the other end is your eardrum. And so clearly this is an open, closed system. So we're looking for the frequencies of an open, closed tube. And we know the length of the tube is 2.5 centimeters, 0.025 meters. And for a prepare step, we're just going to remember what are the frequencies of the mth mode of oscillation. And for an open-closed tube, it's m times v over 4L. And we've said we're going to take as a reasonable value for the speed of sound in air of about 340 meters per second. The length of the tube is 0.025 meters, which is 2.5 centimeters. And so we have everything in hand needed to solve. And we'll do that next. And for a solution, we get this. We're going to look for F1, we're going to look for F3, and we're going to look for F5, et cetera, because we only get the odd modes. We only get m is equal to 1, m is equal to 3, m is equal to 5, and so on. Well, F1 is just equal to 1 times v over 4L. And we said what those numbers were in the previous slide. If we do that, we get 3,400 hertz. Now notice this. F3 is just 3 times v over 4L. Oh, well, that's just 3 times F1. They're just multiples of the lowest frequency, and that is typically true for these sort of situations. So that's just going to be 10,200, and we can use that to find the later frequencies as well. But these are going to be the only 2 at which you have any reasonable sensitivity in terms of your hearing. And for our assessment, looking at these numbers, we will see, in fact, you do get a region of increased sensitivity corresponding to each one of these resonances of the ear canal. So it matches our experience of the world. Now let's take a look at this situation. You know that you sound better when you sing in the shower, and you know that you sing in the shower. Oh, you know that you do. You're by yourself, and so you don't have to worry about admitting it, but you know you sing in the shower. And you sound better when you do it. And why is that? Okay, so suppose you make a shower enclosure by adding glass doors and tile walls to a standard bathtub. And so you end up with an enclosure that is like this. It's 30 inches wide, or 0.75 meters, and 60 inches, or about 1.5 meters long. And you can set up standing waves inside the enclosure. And let's look at what frequencies of standing waves we're going to get on the short axis and on the long axis. Well, first, let's think about what type of system we get. That's our strategized step. So if I do a top view of the shower enclosure, it looks like this. Okay. It's 0.75 meters on this axis, and it's 1.5 meters on this axis. Okay? Well, I'm going to get standing waves on this axis, and I'm also going to get standing waves on this axis. And on both of those axes, there's a hard wall at each end. And so this is a closed tube. You're actually inside the tube. And so I'm going to get resonances of a closed tube along each of the 2 axes. And what we're going to do is this. we're going to prepare, and for a preparation step, we'll remember the frequencies of the modes of a closed tube look like this. It's equal to m times v over 2L. And that's true for values of m is equal to 1, 2, 3, 4, etc. So we're going to get a range of different values. And I want to note as well, okay, that Fm is just going to be equal to m times F1. So we only actually have to calculate the first one, because the second one just has double the frequency and the third has triple, etc., etc., etc. And now we're ready to solve. And to solve, we really only have to do the short, we just have to do F1. So let's do that for the short axis and for the long axis. And if we do that and take a typical value for the speed of sound, what we get for frequency 1 on the short axis is 230 hertz. On the long axis, it's 115 hertz. So the frequencies that we'll get on the short and the long axis are just multiples of those values. And so I'm going to get, on the short axis, 230 hertz, 460, 690, just multiples. I'm going to get F1 and then 2 times F1 and 3 times F1, etc., etc., etc. On the long axis, 115, 230, 345. Now notice this. There's an especially strong resonance at 230 hertz. You get a resonance, the primary resonance on the short axis, the secondary resonance on the long axis. And this is a typical frequency for a baritone voice. So those of you who sing baritone, and by the way, that is me, not me, I am more of a tenor, but early in the morning, my voice is a little bit lower. So early in the morning, I'm probably a baritone. So when I belt out some sound inside the shower, that resonance amplifies those lower frequencies. It just makes your voice sound louder, makes your voice sound richer. And so singing in the shower, it's going to sound better. And I say, go for it. Go for it. It's that pandemic. We can get away with stuff like this. So just treat yourself to a little bit of shower singing first thing in the morning, and you will be happier for the rest of the day. Trust me on this one. Now, the next thing we're going to do in the course is this. That is basically everything we're going to learn. What we're going to do is look back and say, let's take a look at everything we've learned in the course to date, because the final exam is going to ask us to solve a bunch of problems about the world, and it's going to use motion, it's going to use force, it's going to use circular motion, it's going to use torque, it's going to use energy, it's going to use momentum, it's going to use waves and oscillations. Everything we've learned we're going to use to solve problems. And so the last 2 weeks of the semester are going to be devoted to looking back. That is not something Milo does very often, by the way. He is usually a forward-looking guy, but we are going to look back, and we're going to use that to solve a whole bunch of problems. So stay tuned for a lot of that.